Welcome, everyone. I am absolutely thrilled to have you here for this explainer. Today, we are taking an exclusive, under-the-hood tour of the foundational logic that powers our computing systems. We're going to be looking at the legendary 8085 microprocessor. Now, even if you're using a blazing fast smartphone right now, the actual DNA of how that device thinks, how it processes math, and how it talks to memory, well, it all traces right back to the brilliant architecture we're about to decode. So get comfortable because we are going to break down some incredibly clever engineering.
Okay, let's dive into this. We'll start by officially meeting the microprocessor, then we'll move on to memory and I/O mapping. After that, we'll explore the art of instructions, and we'll wrap up with system timing and synchronization.
Now, you might be wondering about our source material. At first glance, it looks like a really dense list of technical engineering exam questions. And well, you'd be absolutely right. But we aren't here to just boringly read from a textbook. We're going to use these exact, real-world questions as windows to decode the 885's specific mechanics. We are translating these complex exam-level problems into pure, easy-to-grasp system logic. Section 1. Meet the microprocessor. To really understand the 8085, it helps to imagine it as a fast-paced, highly organized factory, complete with managers and assembly lines. And this brilliantly illustrates a really common point of confusion, the difference between a microprocessor and a microcontroller. Think of a microprocessor, like our 8085, as just the brain of the factory. On its own, it kind of can't do much. It needs external memory and external input-output devices to actually function. A microcontroller, on the other hand, well, that's the whole package. It has the processor, the memory, the timers, and the I/O devices literally all built in on a single chip. It's basically an entire mini-computer. So inside that brain, the microprocessor needs ways to keep track of what just happened. That is exactly where flags come in. Take the sign status flag, for instance. This is a brilliant little mechanism. After the processor performs any math or Boolean operation, it has to know if the result is positive or negative. It does this by checking the most significant bit. That's the very first bit of the binary result, and storing it in the sign status flag, using a clever hardware mechanism called a flip-flop. If that flag flips to a 1, the processor instantly knows the result is negative. It's basically a tiny instant memo to itself. To really visualize the mechanical rhythm of this factory, let's think about a serial in, serial out 4-bit register. Let's say it starts completely full, with a value of 1111. Our source material actually poses a scenario where, with every single beat of the clock pulse, the system takes the complement, or the exact opposite, of the least significant bit and shoves it right into the most significant bit spot. So, the opposite of that last 1 is 0. On pulse 1, a 0 pushes in, making the whole thing 0111. Pulse 2 pushes another 0 in. Pulse 3, yet another 0. By the time we hit that 4th clock pulse, the entire register has been systematically flushed out to exactly 0000. It's honestly like watching a digital gear turn perfectly into place. Let's move to Section 2 and see how this builds into memory and I/O mapping. All right, so our factory brain is crunching numbers, but it desperately needs a map. The absolute key to that map is the number 16. I want you to remember that number because it is the master key to the 8085's entire kingdom. When the microprocessor needs to find a piece of data, it sends out a 16-bit address across its address bus. In binary, a 16-bit number allows for 65,536 unique combinations. To put that into perspective, that means the processor has over 65,000 distinct mailboxes it can send letters to or read letters from. What's absolutely critical to understand here is a concept called memory-mapped I/O, which our source material explicitly highlights. Instead of having a completely separate, complicated system for communicating with external devices, like a keyboard or a sensor, those I/O devices simply share the exact same 16-bit address space as standard memory. So, to the 8085, asking a sensor for a temperature reading looks exactly the same as reading a piece of standard data from a RAM chip. It's an incredibly elegant and efficient architecture.
Section 3. The Art of Instructions.
Okay, we have our factory, and we have our map, but how do we actually issue commands to the workers? It all boils down to 2 critical pieces of information. The first is the opcode, or operation code. If we strip away the technical jargon for a second, the opcode is simply the action verb. It is the what. Stuff like add, subtract, move, store. For example, STA is an opcode that means store accumulator. It's basically telling the processor, hey, get ready to save this data.
Now, what's really interesting about this is that an action verb alone just isn't enough. If I say store, you're immediately going to ask, store it where? That is the operand. The operand is the where or the who. It's the specific data or 16-bit address that is targeted by the opcode. When you combine an opcode like STA with an operand like the address 2000H, you get a complete machine language instruction, verb and noun, action and target. It's the whole shebang.
Let's actually test this logic out with a brilliant mathematical puzzle pulled straight from our source document. The 8085 needs to multiply a number by 8, but here's the catch. You can only use the RAL instruction, which stands for rotate accumulator left. So how in the world do you pull off multiplication using only a shift command?
Here is the absolute elegance of binary math at work. In binary, shifting all your bits to the left is the exact mathematical equivalent of multiplying by 2. It's just like how adding a 0 to the end of a base 10 number automatically multiplies it by 10, right? So to multiply by 8, you don't actually need a massive complex multiplication circuit. You just shift left once to multiply by 2. Shift left a second time, you've multiplied by 4. Shift left a third time, and boom, you have perfectly multiplied the original number by 8. Literally just 3 simple RAL instructions execute the complex math flawlessly.
Section 4. System timing and synchronization.
A factory can have the very best machines in the world, but if the assembly line isn't perfectly synchronized, the whole thing crashes. So the crucial point is handling those speed differences. You see, the 8085 microprocessor is incredibly fast, but sometimes the memory chips it needs to read from are comparatively sluggish. If the processor just grabs data at its own blazing speed, it'll literally grab empty air before the slow memory is ready to hand it over. The solution? The ready signal. The microprocessor actively checks this pin. If the ready signal is low, the fast microprocessor forces itself to pause and enter wait states until the slower memory finally says, "Okay, I'm ready, here is the data."
And that ready signal is joined by a whole symphony of control signals that manage the system traffic. Our source mentions a few other really critical ones. The ALE, or Address Latch Enable, acts kind of like a traffic cop, telling the system exactly when a legitimate address is on the bus so it can be safely latched or locked in. Meanwhile, the hold and HLDA signals are used for direct memory access. This essentially allows other external devices to politely ask the microprocessor to step aside for just a microsecond so they can transfer data straight into memory without bothering the main brain. So, we've seen how the 8085 managed its internal flabs, macked its vast 16-bit world, executed elegant binary math, and synchronized its own heartbeat, which brings us to a final, pretty fascinating question to leave you with today. If the 8085 needed that simple ready signal just to wait around for a single slow vintage memory chip, how do you think modern 64-bit multi-core processors, which are running billions of times faster, handle this exact same fundamental physics challenge today without just grinding to a halt? The foundation we decoded today is exactly where that answer begins. Thanks so much for joining me on this explainer, and definitely keep questioning how the world around you works.